Understanding AEAD with simple numbers. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, I'm going to explain AEAD encryption using small, simple numbers that anyone can follow. No complex mathematics, no huge cryptographic values, just simple arithmetic that illustrates the core concepts perfectly. The beauty of cryptographic concepts is that they work the same way whether you're using small numbers or massive 256-bit values. By using numbers like 7, 42, or 100, we can see exactly how AEAD works without getting lost in the complexity. We will walk through a complete AEAD encryption example step by step, showing how the plaintext gets encrypted, how authentication tags are calculated, and how associated data gets protected. You will see the actual numbers change at each step, making the abstract concrete. By the end of this presentation, you will have an intuitive understanding of how AEAD combines encryption and authentication into one elegant operation. Let us start with the simplest possible example. Setting up our simple example. Let's start with the simplest possible setup. In the real world, we'd use massive numbers, but for learning, we'll use tiny ones that you can verify with a calculator or even in your head. Our setup. Alice wants to send Bob the secret number 42. She also needs to include Bob's address, room number 101, which must remain visible for delivery, but protected against tampering. This perfectly illustrates the AEAD scenario. Some data needs encryption, the secret 42, while other data just needs authentication, room 101. For our example, we'll use these simple values. The encryption key is 7. In reality, this would be a 256-bit number. The nonce is 3, normally 96 to 128 bits. The plaintext is 42, our secret message. The associated data is 101, Bob's room number. Now, I will use simplified operations to show the concept. Real AEAD uses complex operations like AES and polynomial multiplication, but we will use basic arithmetic that demonstrates the same principles. Think of this as a teaching model, like using a toy car to explain how real cars work. The key insight is that AEAD does two things simultaneously. It transforms the plaintext into ciphertext, which is encryption, and it creates a tag that covers both the ciphertext and associated data, which is authentication. Let's see how this works with our simple numbers. Encryption using counter mode. First, let's see how encryption works in AEAD. We will simulate the counter mode encryption that is used in both AES GCM and ChaCha 20 Poly 1305, but with simple multiplication instead of complex operations. In counter mode, we do not encrypt the plaintext directly. Instead, we encrypt a counter value to create a keystream, then combine it with our plaintext. This is brilliant because it turns a block cipher into a stream cipher. Here is our simplified process. We take our nonce, 3, and create a counter by adding 1, giving us 4. We then encrypt this counter by multiplying by our key. 4 times 7 equals 28. This gives us our keystream value of 28. Now, for the actual encryption, we combine our plaintext, 42, with our keystream, 28. In real AEAD, this is done with XOR, but we will use addition for simplicity. 42 plus 28 equals 70. So, our ciphertext is 70. Notice something important. The encryption operation is reversible. To decrypt, Bob will generate the same keystream, 28, and subtract it from the ciphertext. 70 minus 28 equals 42. He gets back the original plaintext. This demonstrates a key principle of stream ciphers. The security comes from the keystream, not from making the combination operation complex. As long as the keystream is unpredictable without the key, the encryption is secure. Step 2. Creating the authentication tag. Now for the clever part. creating an authentication tag that protects both our ciphertext and the associated data. This is what makes AEAD special. One tag protects everything. In real AEAD, like GCM, this uses polynomial multiplication in a special mathematical field. We will simulate this with simple operations that show the same concept, combining all the protected data into one unforgeable tag. First, we need a hash key. We'll derive this from our main key. 7 times 2 equals 14. In real systems, this would be generated by encrypting a block of zeros, but our simple multiplication serves the same purpose. Now, we will create our tag, step by step. First, process the associated data. 101 multiplied by 14 equals 1414. Then, add our ciphertext. 1414 plus 70 equals 1484. Finally, add the lengths. 1484 plus 1, which is the length of the ciphertext, plus 3, which is the length of the associated data, equals 1488. For our final tag, to keep it small, we will take this value modulo 1000. 1488 mod 1000 equals 488. So, our authentication tag is 488. This tag is like a fingerprint of our entire message. If anyone changes the ciphertext 70 or the associated data 101, the tag calculation will produce a different result. Without knowing our secret key 7, an attacker can't forge a valid tag. This is the magic of authentication. The complete AEAD output. Let's see what Alice actually sends to Bob. This is where we see how AEAD elegantly solves the problem of protecting both confidentiality and authenticity in one operation. Alice's complete message consists of 3 parts. The associated data, 101, is sent in clear text, so the network knows where to deliver it. The ciphertext, 70, is our encrypted secret that only Bob can decrypt. The authentication tag, 488, protects both parts against tampering. Notice that the nonce also needs to be communicated. In our example, Alice could send it explicitly, or it might be derived from a counter both sides maintain. Either way, it is not secret because Bob needs it to decrypt. The complete message might look like 2. Room 101, nonce. 3. Data. 70, tag. 488. Anyone can see that it is going to room 101, but only Bob can extract the secret number 42 from the ciphertext 70. What makes this secure? An attacker might try to change room 101 to 102, redirecting the message, or modify the ciphertext 70 to 71, corrupting the message. But any change would make the tag verification fail. Without the key, they can't compute a new valid tag. This is the elegance of AEAD. One algorithm, one key, complete protection. The associated data feature is particularly clever. It solves real-world problems, like protecting network headers that must remain visible for routing. Bob's verification and decryption process. Now let's see how Bob processes the received message. This is where AEAD's authenticate first, decrypt later approach shows its security wisdom. Bob receives room 101, along with associated data, nonce 3, ciphertext 70, and tag 488. His first job is to verify the tag. This is crucial. He must check authenticity before attempting decryption. Bob recalculates the tag using the same process as Alice. He has the same key, 7, so he derives the same hash key. 7 times 2 equals 14. Next, he processes the associated data. 101 times 14 equals 1414. Then, he adds the ciphertext. 1414 plus 70 equals 1484. He then adds the lengths. 1484 plus 1 plus 3 equals 1488. Finally, he takes modulo 1000. 1488 modulo 1000 equals 488. Bob's calculated tag 488 matches the received tag 488. This confirms that the message hasn't been tampered with. Only now does Bob proceed to decryption. For decryption, Bob generates the same keystream Alice used. Counter equals nonce plus 1, which equals 3 plus 1, which equals 4. The keystream equals the counter times the key, which equals 4 times 7, which equals 28. The plaintext equals the ciphertext minus the keystream, which equals 70 minus 28, which equals 42. Bob successfully recovers the secret number 42. The key takeaway is that if even one bit of the message had been altered, whether it was the room number, the ciphertext, or anything else, the tag check would have failed. This would have led Bob to reject the message without ever attempting decryption. What happens with tampering? Let's see what happens when an attacker tries to tamper with our message. This demonstrates why AEAD is so effective at preventing both passive and active attacks. Scenario 1. An attacker intercepts the message and tries to redirect it from room 101 to room 102. They change the associated data, but cannot update the tag because they do not have the key. When Bob receives this tampered message, he calculates 102 times 14 equals 1428, which is different from the original 1414. Continue the calculation. 1428 plus 70 plus 1 plus 3 equals 1502. The tag equals 1502 mod 1000, which equals 502. The calculated tag of 502 does not match the received tag of 488. The message is rejected. Scenario 2. The attacker tries to change the ciphertext from 70 to 71, hoping to corrupt the secret. Bob calculates 101 times 14 equals 1414, then 1414 plus 71 equals 1485. Continue. 1485 plus 1 plus 3 equals 1489. Tag equals 1489 mod 1000 equals 489. Again, 489 doesn't match 488. Message rejected. The attacker is stuck. They can't forge a valid tag without the key. They can't modify any part of the message without detection. They can't even replay an old message if Bob checks for nonce reuse. This comprehensive protection is why AEAD has become the gold standard for secure communication. Now let me show you why nonce reuse is catastrophic in AEAD. This is the one thing you must never do, and our simple numbers make it crystal clear why. Suppose Alice sends two different messages using the same key, which is 7, and the same nonce, which is 3. The first message has a plaintext value of 42. The second message has a plaintext value of 55. Both messages use the nonce value of 3. For both messages, the counter is the same. Nonce plus 1 equals 4. The keystream is the same. 4 times 7 equals 28. Message 1 ciphertext. 42 plus 28 equals 70. Message 2 ciphertext. 55 plus 28 equals 83. An attacker who sees both ciphertexts can compute 83 minus 70 equals 13. This equals the difference in plain texts. 55 minus 42 equals 13. The attacker has learned something about our secrets without knowing the key. Worse, in real AEAD with XOR operations, nonce reuse allows the attacker to compute the XOR of the plain texts. With enough reused nonces, they can recover the keystream and break the encryption entirely. For authentication, reused nonces can allow forgeries. This is why every AEAD implementation is obsessed with preventing nonce reuse. It is the cryptographic equivalent of crossing the streams, and it must never happen. A simple example illustrates why. Reusing the nonce means reusing the keystream, which leaks information about our secrets. Scaling up to real numbers. Now that you understand AEAD with small numbers, let's briefly see how this scales to real cryptography. The principles remain exactly the same, only the numbers get bigger. In real AES-GCM, our key of 7 becomes a 256-bit number. Our nonce of 3 becomes a 96-bit number. Our simple multiplication becomes AES encryption. Our basic modulo arithmetic becomes polynomial multiplication in GF2 to the power of 128. The security comes from scale. With our toy example, an attacker could try all possible keys, perhaps 1 to 100, quickly. With 256-bit keys, there are more possible keys than atoms in the universe. Our simple tag could be forged by luck, a 1 in 1,000 chance. Real 128-bit tags have an astronomically small chance of being forged. But the beautiful thing is that the algorithm works the same way. Real AEAD still generates a keystream from the key and nonce, combines it with plaintext to create ciphertext, calculates an authentication tag covering all data, and verifies the tag before decryption. Our simple example with small numbers reveals the elegant design of AEAD. Whether you are encrypting the number 42 or a 4K video stream, the process is identical. Only the size of the numbers changes. This scalability from toy examples to production systems is a hallmark of good cryptographic design. Summary: AEAD simplified. We've journeyed through AEAD using simple numbers, and I hope you now see how elegant this system is. Let's recap what we've learned using our small number example. AEAD combines encryption and authentication seamlessly. With just one key 7 and one algorithm, we protected both the secrecy of our message 42 and the integrity of all data, including the delivery address 101. No need for separate operations or multiple keys. The counter mode encryption, plaintext plus keystream, provides confidentiality while being efficient and parallelizable. The authentication tag protects against any tampering, whether to the encrypted data or the associated data. The nonce ensures each encryption is unique, preventing pattern analysis. We saw how tampering with any part of the message causes tag verification to fail, stopping attacks cold. We also saw why nonce reuse is catastrophic. It is the one rule that must never be broken. The system fails safely. Bad tag means no decryption, period. The same principles we demonstrated with single-digit numbers apply to real AEAD systems protecting your bank transactions, video calls, and web browsing. The numbers get bigger, the operations get more complex, but the elegant design remains the same. Next time you see AES-GCM or CHA-20 Poly 1305 in a security setting, remember our simple example. At its heart, AEAD is just doing what we did here, using one key to provide both secrecy and authenticity in one beautiful operation. Thank you for your attendance. Please consider subscribing to the channel.